Hi everyone, my name is Lara and I completed my Pawsey internship over the 2022-2023 summer break. While my original background is in biochemistry, I've always had an interest in the computational side of science, so this opportunity was perfect for me as my project combined with biochemistry and computer science. My project was looking into the effect of cryoprotectants on cell membranes, and this was the poster that I produced. To start off, we need some background. The process we're interested in is cryopreservation, which is the storage of biological materials using low temperatures. During the process of freezing and thawing these materials, the cell's membrane is prone to losing its structural and functional integrity. So what we can do is we can add cryoprotective agents to reduce this damage. Our specific question was, how do the cryoprotective agents arabitol, iodotil, and erythritol impact the area per lipid of a membrane at different hydration and concentration states? To explain, area per lipid refers to the space that a single lipid takes up in the membrane. What we aim for is to have the area per lipid be relatively large enough to support membrane fluidity before cryopreservation, so that it can maintain its functionality. We want the membrane to be fluid enough so that it can allow for the transport of molecules into and out of the cell. So how do we do this using supercomputers? We can use molecular dynamic simulations of a section of a membrane to see how all these molecules interact at a molecular level. We combine files which describe the atomic details of the membrane, water, and cryoprotectant we're studying into a single system. We can then run these systems on the supercomputer. Running simulations like these on a computer like my own or yours would take months, while supercomputers allow us to run these in a matter of days. We first run energy minimization and the molecules fall into the preferred energy levels. We then run heating from 0 to 300 Kelvin and then let these systems reach equilibrium. Then we can finally run the production step, which is what allows us to produce our experimental data. At the bottom, I have a figure which shows all the systems that I analyzed. So using lipid 17 and gap force fields, which are mathematical formulas which determine everything that the atoms in our systems will do, we have two hydration states, full hydrated and dehydrated. For each hydration state, we then have two concentrations, 0.4 and 0.8 molar. And for each concentration, we have the three cryoprotective agents to analyze. So you can see that this becomes a lot of work, having 12 systems overall. So next up, I have my results. First off, I have a visual representation of the systems at the end of the production for both hydration states of the 0.4 molar arabitol system. So on the right is the full hydration system, and you can see if you look at the orange head groups that they're quite shifted apart compared to the dehydrated state, which looks more compressed. This shows the beginning of a trend where full hydration is found with higher area per lipid across all systems. Next up is table 1. This just proves that I swear I did run every single system. The main takeaway is that area per lipid seems to be higher for hydrated states, higher concentrations, and where cryoprotective agents are introduced into the system. To finish off, figure 3 shows how the two arabitol 0.4 molar systems have their area per lipid fluctuate across their runtimes. Again, you can see the consistently higher area per lipid for the fully hydrated system in dark blue. So overall, membrane expansion or a larger area per lipid suggests for higher fluidity, which is essential for the membrane's function in providing molecular exchange for the cell. As we can see from our results, dehydration shrinks the membrane, but this effect is counteracted by the addition of cryoprotectants. As all I reported was on area per lipid, to finish off for future perspectives, we aim to investigate the specific interactions of each cryoprotective agent with the membrane to determine differences in their mechanism of actions. This would be things such as hydrogen bonding and mass density profiles. So that concludes my internship, but if you have any further questions or would like to get in contact for any other reason, feel free to reach out to me via email. Thank you.